Good morning. We were discussing random mismatch. Which basically indicates a phenomenon where identical components, that is, you have exactly the same layout, everything, they have different values. This is because of some statistical fluctuations in different properties, such as the level of doping, dimensions, etc. Okay. So what happens is if you have identical layouts, you still have different values, such as you have identical width and length for resistors, you still have different values for them and so on. And those values, they fall on a Gaussian distribution like many natural phenomena. And essentially, the mean value is the nominal value that you want to design. And the variance, it turns out, depends on the physical size of the component. Okay. So in our case, we have only control over W and L. So we describe the variance as being inversely proportional to the area of the component. Okay. This is true for every component. And the parameters of interest are the sheet resistance of resistors or capacitance per unit area of the capacitance of not sheet resistance, I'll say the resistance value, the capacitance value. And for the MOS transistor, you have the threshold voltage and the current factor. Okay. And that body effect coefficient gamma also follows the same distribution. Normally, we don't use it in hand calculations, but that is another parameter that varies. Okay. So for a resistor, the actual value will be R naught plus delta R, where R naught is the nominal value. And it turns out that this variance, which is basically the variance of the normalized error. Okay. So this is AR square by WL, where AR is some constant of the process. Okay. Again, for the capacitance, you have C naught plus delta C and sigma C square, which is the variance of delta C by C naught is AC square by WL. Okay. This is true for every component. I'm only going to show the components that we normally use. And for a MOS transistor, you will have the current factor, which is mu C ox W by L, the whole thing combined, to be beta naught plus delta beta, and then the threshold voltage to be VT naught plus delta VT. For the current factor, what you specify is the variance of the relative error, okay, which like everything else is inversely proportional to area. For the threshold voltage mismatch, it doesn't make sense to indicate the relative error, because the absolute error doesn't mean, the absolute value of the threshold voltage doesn't mean much, and it could even be zero. And if you have a zero valued parameter, you cannot really specify the relative error, right? So sigma VT square is simply the variance of delta VT, and that is AVT square by WL. Okay. So this is just the variance. Now, what is it that you have to do? You have to analyze the effect of this error in any circuit. Okay. Now, how do you do that? Let's say you have a circuit with resistor R naught and capacitor C naught and a MOS transistor. I mean, you will have many components. I'm just showing one each. Okay. So how do you find the effect of error in this resistor? What do you do? We discussed this, right? So what is it that we do to analyze the effect of right? So you find the nominal current that is flowing through this. Okay. Right. And you can also do it in terms of the nominal voltage. Okay. Now these can be in any domain. This could be the operating point if you are looking for effect of mismatch on the operating point. But it could also be the signal in the time domain or in the frequency domain. Okay. That is, you could be looking at this VR naught of S, that is, you are doing Laplace transform analysis, and then you want to see what the effect on the output is of that error in that resistor. So it can be in any domain. Okay. So now what is it that you do? You can either replace the resistance by a series combination of the nominal resistance R naught and a voltage source that denotes that represents the error due to mismatch. What is the value of that voltage source? I into delta R. So remember, this is given in terms of relative error. So how would we represent that voltage? So it's basically VR naught times delta R by R naught. Okay. So this is the source from which you calculate the output. The output could be somewhere. So let's say this is the output, and you can find the transfer function or the gain from that voltage source to that one. Okay. Similarly, for the capacitance, what would it be? Let's say we do this in the Laplace domain. You have the nominal capacitance C naught. What is that additional source? For the resistance also, by the way, we can have an equivalent current source instead. Okay. What will be that value of that current? What is it going to be? I mean, the mismatch in the resistor can be represented as a voltage source in series with the resistor or a current source in parallel with the nominal resistance. What is that current value? Yeah. So again, give me the expression in terms of the relative mismatch. What is it? So this will be IR naught times delta G by G naught in that direction, right? Is that correct? And which can be written as minus IR naught delta R by R naught. So it has to be in the other direction. That's all. Okay. Actually, all you had to do is just take this and feminize that one, right? Now, what is it for a capacitor? Maybe the current source is easier for a capacitor. What is it? If I have a capacitance like that and a current source downwards, what will be the value of this? IC naught times. It's basically the admittance of this divided by admittance of that extra part divided by the nominal admittance. So it will be S times delta C by SC naught, which is basically delta C by C naught. Okay. Is that fine? So what will be this voltage source? What is that going to be? So again, you just convert this into the Thevenin equivalent and you will get minus Vc naught times delta C by C naught. Okay. You can use any of them, and just to be correct, I am showing all these signs. When you are only calculating the effect of mismatch on a single output from all these different components, the mismatch from different components will be uncorrelated. So these plus and minus signs don't matter. But of course, just as a good practice, make sure that you get these signs correct. Okay. So essentially, the effect of mismatch can be obtained from small signal incremental analysis with these sources. The mismatch effect can be represented as an incremental source at the operating point. Okay. At that, when I say operating point, it's not just DC operating point. It's with whatever you have, operating point plus signal, anything. Okay. So the same current in with this delta, the delta component should be used to get this additional source. Okay. Any questions? So you can do this now. This is scalable for any circuit complexity, right? You can't write the expression in terms of every component and then put deltas everywhere and then try to expand it, etc., etc. That is very difficult. This is a lot easier. Okay, and it's the same circuit analysis that you do with a source here. You can do it with this mismatch related source. What would we do for the MOS transistor? What would it be? So this MOS transistor has some error in the current factor delta beta and some error in the threshold voltage delta Vt. So how should we represent these? Again, obviously, I want to represent these as represent the MOS transistor as the nominal MOS transistor plus some additional sources, so that I can do circuit analysis to find the effect. Okay. So what will how will I represent the effect of delta Vt, for instance? Current source where? What is the most natural way to represent the effect of delta Vt? What do you think it is? So the MOS transistor's current is beta with that the nominal current is beta naught by 2 VGS minus VT naught squared. Okay. The actual current, which is ID naught plus delta ID, would be beta naught plus delta beta divided by 2 VGS minus VT naught minus delta VT squared. Okay. So just from this expression, you can see that you can combine these, right? VGS minus delta VT and have this delta VT over there. Okay. So then what happens is whatever voltage is applied here, which is the actual VGS, will appear as VGS minus delta VT to this ideal transistor. Okay. And what is this part? This is beta naught plus delta beta by 2. So which is basically the nominal value, beta naught by 2, 1 plus, right? Okay. And that can be represented as a current source, which is ID naught times delta beta by beta naught, where ID naught is the nominal current. Okay. So it's 1 plus delta beta by beta naught times the nominal current. Is this fine? So we'll need two sources in a MOS transistor because there are two mismatch effects, one in the current factor and one in the threshold voltage. Okay. Is this fine? So we can use it as is, or we can even combine the two. So let's say I want to combine both effects as a voltage in series with the gate. So what would that voltage source be? That is, I don't want to have two sources, but I want to have a single source. What would that voltage source be? Minus. Why minus? Yeah. So basically, this to get this additional incremental current, the incremental gate source voltage must be this divided by GM. Okay. So VGS has to increase by so much. Now this the way this voltage source is defined, VGS is decreasing by that much. So this should be delta VT minus ID naught by GM times delta beta by beta naught. Okay. Is this okay? And how much is ID naught by GM? How much is it? What is the expression for GM? I mean the relevant expression for GM here. Yeah, it's 2 times ID naught by VGS minus VT. So this is VGS minus VT by 2, assuming this is in the strong inversion region. Okay. If it's in the weak inversion region, this would be ID naught by eta times the thermal voltage, and this would be eta times thermal voltage divided by, I mean, that's all, eta times thermal voltage. Okay. So this can be alternatively written as delta VT minus VGS minus VT, that is gate overdrive by 2 times delta beta by beta naught. Okay. And of course, whether you choose a voltage source or a current source, it's purely based on convenience. So we can instead have a single current source in parallel with the drain to represent both mismatches. And what would that value be? What would it be? ID naught times delta beta by beta naught minus GM times delta VT. Okay. So again, you calculate the gain from these different incremental sources to the output. And what is it that you want to find out? Usually it is the variance of the output. Okay. So it will be the variance of these, this one or that one times some number, square, right? Whatever scaling factor you get, you have to square that and multiply here. Okay. Any questions on how to calculate the effect of mismatch? So you calculate the so here let me just show one particular form for completeness. For the MOS transistor, we have delta VT minus ID naught by GM delta beta by beta naught. So you calculate the transfer functions from all these sources, from this capacitor to the output, from this source to the output, and so on. And you will get some expression. Okay. So you may get something like the change in the output voltage would be some constant times change in the resistance plus some other constant times the change in the capacitance plus some third constant times delta VT plus some fourth constant times delta beta by beta naught. So now what is it that you do? So you want to calculate the variance of this will be, what is it? Yeah. So I'll just show it like this. These could be, depending on the domain, I mean, it could be some complex number. So it's the magnitude square of K1 times sigma R square plus magnitude square sigma C square magnitude square of K4 times sigma beta square. And these, from the component sizes and process information, you can find out. Okay. So finally, this is how you find the effect of mismatch in any circuit. So again, finally, all you need to know is small signal, basically linear circuit analysis, which is small signal incremental analysis. Okay. Any questions here? So now we saw that sigma square of anything is inversely proportional to the area. Okay. So let me just show it as it fits for a resistor, but for everything it follows the same. And if I plot this on a log scale, what will the curve look like? What will it look like? Y equals? Yeah. So it will be a straight line with a negative slope. It will do that. Okay. So for every, let's say, doubling of, or if this changes by 10 times, the area increases by 10 times, the mismatch variance also falls by 10 times. Okay. Now there is one more effect that comes into this matching, which of course is hard to calculate. We won't do it, but this one implies that if you go on increasing the area, right, the mismatch will go on decreasing. Okay. Of course, you can't increase it by, I mean, you can't reduce the mismatch by very large factors in practice because you can't have area going out of control. As I mentioned, on an integrated circuit, area is cost. Okay. But even besides that, there is another thing that affects matching. So let's say you have two resistors close to each other, right next to each other, versus one resistor here, one somewhere far away. Now it turns out that the ones that are closer to each other match better. So there is some distance dependence. It's very hard to model by hand. We won't do that. If you have detailed process modeling, you will have that as well. So this has better matching and this has worse matching. But at least this doesn't sound unreasonable. I mean, intuitively, you may feel that, of course, components that are closer to each other have very similar processing, whereas the ones farther from each other may have a larger variance. Okay. So what do you think will happen now if I go on increasing the area? Now, of course, here I'm talking about two components. So what is the relationship between this and the curve I have drawn above? What do you think will happen? So what happens is basically when you make a component with a larger area, essentially maybe first you had, let's say, a single resistor, and then you double its dimension in both directions. Okay. So clearly, if you divide this into 4 pieces, you can see these two are close to each other, this and this are further apart. If you make a very large one, right, this also can be thought of as some combination of identical units, but you can see the distance between this and that are quite large. So it's not the same as the distance between adjoining pieces. Okay. So the matching between this one and that one will be much worse than the matching between those two. So what happens is this doesn't keep going down monotonically. It goes down to some extent and then it flattens out. Okay. So you can't reduce the mismatch below a certain value because although you are willing to increase the area, I mean, the area is so large that this part and that part are quite far from each other. Okay. And it turns out in practice, on an IC, capacitors have the best matching. Where this sigma C could be of the order of, it again depends on the size, but it can be of that order. Okay. And the resistors are, of course, if you take a very small capacitor, obviously its matching will be worse than a large capacitor. But still, this is sort of the best case, the saturated value that you can get. Okay. Resistors are the next, they may be of the order of 0.1%. So again, these are all process dependent. So these are not like fundamental constant, right? So if a process is specifically designed to improve the matching of some component, you could get better. And the MOS transistors are the worst of the lot. Okay. So this has implications on circuit architectures also. So one of the circuits that I think you know and which also employs identical components is a digital to analog converter. The way a digital to analog converter works is you have a number of components and you switch a selected number of them in to give you some voltage or current. Okay, you don't need to know the details, but for instance, you can have a resistor ladder and you can have switches to connect one of the taps of the resistor ladder to the output. Okay, depending on which switch is on, you will get a voltage that is proportional to the digital code. Okay, so clearly for these things, something that is based on capacitors would be the best because there mismatch means you will have error. Okay, so similarly, the next best would be resistors and the next would be MOS transistors. Okay, any questions here? But these numbers are just indicative, but the order of how good the matching is correct. That is true for most technologies. Okay. Any questions on this mismatch calculations and so on? So let's say I have this circuit and this is I naught. This is I out and I have a 1:1 current mirror. Okay, they are identical. Both have sizes W by L. Okay. So now I make this current mirror. These current mirrors are used very widely in circuit design. Okay. So what I want to find out is, I mean, again, my idea was that I'll get exactly the same current, but now we know because of mismatch it may not be. So please find the variance. Nominally, what is the output current? It should be I naught, right? But it is not going to be. So please please calculate the variance. Practice for all the one of the things to decide also is how you will model the Represent the mismatch of each component is now suitable in calculator. Yeah. More than will not be Now the first thing is to, of course, represent the error in each of M1 and M2 as appropriate sources. You can use any of the representations. That is, you can have a voltage source at the gate for delta VT and a current source between the drain and source for the delta beta effect. Or you can combine both into either a voltage source at the gate or a current source from drain to source. All three are possible, right? All three that we saw. Okay. So we have two separate sources here and a single source at the gate or a single source at the drain. Okay. Of course, you should get the same answer with all of them. But looking at this circuit, which one might be the most convenient? Current source. Why? I mean, it's a current mirror after all. So if I have some delta I1 here, some delta I2 there. Okay. So first of all, let's say I don't have anything and I have ideal components. What will be I out? What will be I out? So the nominal condition, this will be just I naught. And if I have some current delta I1 there, what will be the output current? What is it? What is it? What is the total current? I naught? I naught minus delta I1. Okay. And if I have a current delta I2 over there, this will be plus delta I2. Okay. So all I have to do is calculate the variance of minus delta I1 plus delta I2. Okay. And how much is delta I1? How much is delta I1? So it's delta beta 1 by, you have to use different indices for different components because they are physically different components, they have uncorrelated mismatch. Delta beta 1 by beta naught times I naught, the nominal current, then minus GM. GM is the same for these two, so I will use just GM naught times delta VT 1. Okay, so that is delta I1. So I have to take minus this. I'll keep the signs correct for now. We know that it really doesn't matter. Plus delta I2, same expression, delta beta 2 by beta naught times I naught minus GM naught times delta VT 2. Okay. So this whole thing is the error in the current. And if you want to calculate the relative error, you have to divide this by I naught. Okay. So this is now the relative error. And you can calculate the variance of this. It's very easy. I mean, the four terms are uncorrelated from each other. You simply add up the scaled variances from each one. Okay. So what will I get? So the first one would be sigma beta square, and the next one would be GM naught square times I naught square times sigma VT square. Okay. Sigma VT 1 square actually. Similarly, okay, and they're identical transistors, so sigma beta 1 square and sigma beta 2 square are the same. Similarly for variance of VT. So the variance of delta I naught by I naught in this 1:1 current mirror is basically 2 times A beta square by WL plus 2 times AVT square by WL times GM naught by I naught square, and this itself would be what is maybe I'll just write the GM naught by I naught. What was this? This is VGS minus VT square by 4. What is it? Oh, sorry, the opposite, right? So this is in the strong inversion region, and that is in the weak inversion region. Okay. So now you have the expression for variance, and then you can do what you want with it. Okay. Is that fine? So this is an example. Now even here you can see what does it, I mean, maybe there is some design implication. So first of all, should you operate in strong inversion or weak inversion for lower mismatch? Strong inversion. Why? So VGS minus VT should be above 150 millivolts in strong inversion. In fact, maybe it is more illuminating if I write it as half of VGS minus VT should be above 75 millivolts. Okay. Whereas what is the thermal voltage? 25 millivolts. Even if eta is 2, it's only 50 millivolts. So clearly in weak inversion, the effect of the threshold voltage mismatch will be larger. Okay. In a current mirror, again, this conclusion is different for different circuits. For a current mirror, the effect of the threshold voltage mismatch will be larger in weak inversion than in strong inversion. Okay. So if mismatch is the only thing that you're after, then it is better to operate with strong inversion with as high a VGS minus VT as possible. Okay. So finally, the mismatch will be limited only by the current factor mismatch. Okay, that is not related to the operating point, right? You will always get that A beta square by WL. The variance of the current factor mismatch will always be there. But the threshold voltage mismatch is lower in strong inversion region. Okay. Now, let's say you do that, you go on like making VGS minus VT larger and larger. What would be the disadvantage? Is there any, or I can keep doing this? Why? Where did the capacitance come in? So first of all, I didn't ask a very well controlled question. So if you want to mirror a given current, okay, and if you want to mirror a given current, so how would you change things? Let's say you have designed some current mirror, its mismatch is too high, and you want to reduce that by some amount. What are all the things you can do? One is just go and increase the area, right? That will work. But let's say you are not allowed to do that. You have some area constraint. You want to keep the area the same. So then what is it that you can do? How? What will you do? I mean, again, as a designer, you have the freedom to pick this W and L. So what will you do? Reduce the W by L ratio. So basically, let's say you want to keep the same area, you can keep WL product the same, but reduce W and increase L. Okay. So what will that do? That will increase the overdrive voltage VGS minus VT and reduce that component of the mismatch. Of course, once it becomes insignificant, there is not much you can do beyond that, right? Okay, what's the disadvantage of that? Is there any? So now, basically, when you have a current source, right, the ideal what is the IV characteristic of an ideal current source? It's a horizontal line. Okay. For a MOS transistor current source, what will it be? If this V is the output voltage, if this is VDS, what is it going to be? So it will be constant current down to some value. What value is that? VGS minus VT, and after that it doesn't behave like a current source. In fact, every current source will have some limited, every real current source will have some limited voltage range. That's called the compliance of the current source. So if you go on increasing, if you overdo this, let's say I want precision, so I'll go on reducing W and increasing L to increase VGS minus VT. What happens is the compliance decreases. Okay. So there is a trade-off between precision, which is this mismatch error, and this voltage compliance and so on. So now if you're operating with a low voltage supply, you cannot increase this VGS minus VT too much. Then you have very little signal swing left. Okay. So there are trade-offs between all these things. But it is in general true that like if you are making current mirrors, you will have lesser mismatch if you operate in the strong inversion region. And what is really happening when you reduce W by L? Sorry, you keep W by L the same, but you reduce W and increase L. What happens is the GM of the transistor reduces. So if there is an error in the threshold voltage, GM represents the gain from that to the output current. Okay, so if you have a smaller GM, obviously you will be less sensitive to the error. Okay, that's the idea. Any questions here? So this is a simple example. You can extend this. You can, for instance, try what to see what happens with a 1:n current mirror instead of a 1:1 current mirror and so on. Okay. So the bottom line is mismatch can be analyzed using small signal incremental analysis, which is something you are very familiar with, which is what you always use. It's just linear analysis. Only thing is the mismatch has to be represented by appropriate sources. That is also easy. It basically depends on the nominal values of the currents and voltages and some mismatch related quantities. And then you need to know the variance of the mismatch of the component that you get from the process constant and the dimensions. Okay. Any questions here? So we have seen process and temperature variations, which we consider to be common to all the components on a chip. And then now we have mismatch, which is really different for each component. So we cannot specify it individually. Only thing is we can specify some statistics of it. So for instance, you are asked to make a current source and you can calculate this variance of or standard deviation of delta I naught by I naught. And then you can tell like how many, what fraction of the current sources will be within some specification. Okay. We'll say within 0.5% of nominal value and so on. Okay. So the point is we know how to calculate it. Now for any circuit, you should be able to calculate the effect of mismatch from small signal analysis. Any questions? Now, what is this random mismatch all about? Let's just recall. Now, essentially, if I have this and if I measure this current, obviously it should be V by R. And if I apply some fixed voltage, then this should be V naught by R. Okay. Now, if I have a large number of different resistors and an IC, and I connect V naught to all of them, right? I should expect V naught by R in all the resistors, right? But what happens instead? What did we say? They'll all be, I mean, slightly different from each other. They'll follow some distribution. We know how to calculate the distribution also. That is, we calculate the variance of that distribution, right? Now, there is one more thing beyond this. One, of course, essentially what is happening is the value of R itself is different. Okay. Now, for now, let's forget this random mismatch. Okay. And let's assume that all the resistors are identical. Then what would I have expected? In every resistor, I should have had a current V naught by R. Okay. I'm just showing like some examples, all of them. Now it turns out, even if the resistors are exactly identical, this will not be the case. Okay. So what happens is, if you are able to measure the instantaneous current precisely, what you will see is, first of all, the current is not constant with time, even if the voltage is constant with time. Okay. So you will have something like this. The currents will be different at different instances of time. At the same instant, they'll also be different in different resistors. Okay. So this is what is known as random noise, and we'll take that up next. Okay. So the current will not be the same at every instant of time, even if you apply a constant voltage with time. And even if you apply the same voltage to different resistors and measure the currents at exactly the same instant, the currents will be different from each other. Okay. We'll see how to analyze this and characterize the effects. Any questions?